This is the second video on solving different types of equations with all the algebra we know. Last time we covered radical equations and rational equations. This time we're going to look at what's called absolute value equations. And then we'll look at one other thing after that. As far as it goes, for an absolute value equation, again, we all know what an absolute value is. When we talk about absolute value equations, we mean equations with absolute values with an x inside of them. So something like the absolute value of x plus 2 plus 3 equals 7. Or I don't just have an absolute value, I have an absolute value with an x inside of it, which causes an issue. But as far as it goes, we can use the same principle that we used before. If something causes a problem, in this case the absolute value, we isolate it so we can deal with it. So if we do that right here, subtract the 3, we get the absolute value of x plus 2 equals 7 minus 3, 4. And the question is, what exactly do we do from there? And there's an idea here that makes this easier to understand. If we think about the graph, which we will cover later in the semester in greater detail, but for right now, the absolute value graph just looks like a V, like this, if you haven't seen it before. Where the absolute value of 1 is 1, 2 is 2, negative 1 is 1, negative 2 is 2. So for the sake of argument, suppose I want to know where the absolute value of x equals 5. One thing I can do is find the point y equals 5, we'll say it's right there, and then draw a horizontal line through that point. And there's 2 points on the graph that give me an absolute value of 5. Clearly, it will be x equal to 5 and x equal to negative 5 because they both have an absolute value of 5. All that really means is the absolute value of x equals 5 means x equals 5 or negative 5. If I wanted to generalize that, the absolute value of x equals any number a means x equals a or x equals negative a. Once I understand that, I can use it to solve the problem over there. So, we just said the absolute value of x equals a means x equals a or x equals negative a. So use that. This is not the absolute value of x, it's the absolute value of x plus 2, but it doesn't matter. The absolute value of something equals 4 means that something equals 4 or that something equals negative 4. And now I just solved both equations. In this case, if x plus 2 equals 4, then x equals 4 minus 2, 2. In this case, if x plus 2 equals negative 4, x equals negative 4 minus 2, negative 6. And I get two solutions. Again, just like we've been saying, check to make sure they work. These absolute value equations will give you two solutions a lot. We saw that from the graph. But just check, there's still times we can get extraneous solutions. In this case, if I plug in 2, I get 2 plus 2, which is 4. The absolute value of 4 is 4. 4 plus 3 is 7. That definitely works. If I plug in negative 6, negative 6 plus 2 is negative 4. The absolute value of negative 4 is positive 4. 4 plus 3 is 7, and I'm good. So in this case, they both work, no extraneous solutions. As far as it goes, as far as little things you guys have to memorize and use, you're going to need this right here. The absolute value of x equals a means x equals a or x equals negative a. A lot of times on exams, and not necessarily on homework when you have the book available, but on exams, students will solve these out and only give me the positive solution because it's really easy to see. And they completely forget the negative one right here and only get half the problem right. Just make sure you solve both of those out for your absolute value equations. So, suppose we have 3 times the absolute value of 2x plus 5 plus 4 equals, we'll go with 19. Solve that out. Yes, it might look slightly more complicated, but we understand the principle now. Isolate the thing that causes a problem. So, to isolate the absolute value, subtract the 4. We get 3 times the absolute value of 2x plus 5 equals 19 minus 4, 15. Now I want to isolate this, so divide the 3. The absolute value of 2x plus 5 equals 5. Now I have this in the form I want. Absolute value equals a number. So now I get two possible solutions. 2x plus 5 equals 5, or 2x plus 5 equals negative 5. And then we just solve both of them. For this one, if I subtract the 5, I get 2x equals 5 minus 5, 0. Divide the 2, x equals 0. For this one, subtract the 5, 2x equals minus 5, which is minus 10. Divide the 2, x equals negative 10 over 2, which is negative 5. And then lastly, like before, we check to see if they're extraneous. This one I'll actually write out the check since there's a little bit more algebra involved. If you plug in 0, we get 3 times the absolute value of 2 times 0 is 0. So that's 0 plus 5 plus 4 equals 19. 0 plus 5 is 5. The absolute value of 5 is 5. 5 times 3 is 15. So I get 15 plus 4 is 19, which is certainly true. For the other one, if I plug in negative 5, I get 3 times the absolute value. 2 times negative 5 is negative 10 plus 5 plus 4 equals 19. Then I'm left with negative 10 plus 5, which is negative 5. The absolute value of negative 5 is positive 5. 3 times 5 is 15. And I get 15 plus 4 is 19, which also works. So again, both solutions work. Hey, as far as it goes for absolute value equations, that should give us a good working knowledge of everything going on. Now there's one more type of problem we want to look at, and it's what's called quadratic in type. Or put another way, equations that aren't quadratic but kind of sort of look quadratic. And as far as it goes, if we have something like this, x to the 4th minus x squared minus 6 equals 0, that is not a quadratic. That's raised to the 4th power, it's a quartic. But if we think about it a little bit, it kind of sort of looks like a regular quadratic equation that we've seen. X squared minus x minus 6 equals 0. I mean, you have the 0 here, you have the negative 6. The only difference is this has an x and an x squared, that has an x squared and an x to the 4th. But if I take this middle term and square it, I get that first term. That's what makes this a quadratic. Here, if I take this middle term and square it, x squared squared is x to the 4th, the first term. So even the pattern is the same between the two. And all that really means from a math perspective is we call it quadratic in type, meaning it looks like a quadratic, so I might as well solve it like I would solve a quadratic. If this was a quadratic, I would solve it by factoring. So I would say, get my factors. I need two numbers that multiply to negative 6 that add to negative 1. That's easy. Negative 3 and positive 2. The only thing that changes is this leading term here. Before, I used x and x to get x squared. Now I need an x to the 4th. I just use the middle term, the x squared. X squared times x squared will give me my x to the 4th. So you set it up and factor it the same way you would factor a quadratic. The only difference is now I take my factors and set them to 0. X squared plus 2 equals 0. X squared minus 3 equals 0. And now I'm not done. When you solve the quadratic, you're pretty much done. Now these factors of each quadratic, I have to solve those. But these are pretty simple. Here, subtract the 2. X squared equals negative 2. Square root both sides. we get x equals plus or minus the square root of negative 2, which we know means the square root of 2i. Here, x squared minus 3 equals 0, add the 3, x squared equals 3, square root both sides, x equals plus or minus root 3. And now, just keep in mind, plus or minus root 2i, plus or minus root 3, that's 4 different solutions. There's a fundamental rule of algebra. We haven't covered it yet, but we will eventually. Whatever the highest degree of x is in your problem, that's how many solutions you should get. That's a 4th degree. 2 solutions, 2 solutions. I got the 4 I want. All things being equal, we are not going to use this trick a lot, but it does pop up in problem solving, so I wanted to make sure you guys have at least seen it and understand how to solve the problems. Do exactly what makes sense when your brain sees this, and then just have to do some extra stuff at the end.